Everyone, thank you for coming to my talk. Dive into Flytekit's internals. It's Python SDK to quickly bring your code into production. This Flyte is like an orchestrator. Like Airflow, Dagster, Prefect is in that realm of tooling. This talk is about focus around the Python SDK and how the design decisions made to build a Python SDK so that you can run stuff into in our cluster in production. And Flyte is one of the key points of Flyte is that you could write code in Python like, in your local machine and quickly with one command bring it into a cluster and then run that in a cluster. So that's the selling point. And now we're going underneath the covers to see how it works, right, from the Python SDK point of view. Talk is available on GitHub. There's a QR code to it. Again, about me, I'm Thomas, JFan. I'm a maintainer of scikit-learn for open source. Day job, I'm a member of technical staff at Modal. I used to work on Flyte and the Python SDK, so this is like all the learnings I've taken from working on the project and put it into slides so that if you want to build an orchestrator, here are the things you need to think about, right, in Python. So before I begin diving into Flyte, I want to give a broad overview of what Flyte is, so why people choose Flyte out of the other orchestrators, and then a quick walkthrough of what a user experiences when they use Flyte. And after that, with that context, dive into how it works. So that's my breakdown of today's talk. Now, why Flyte? Flyte is known for being reliable. Once you have a working workflow written down, it will work. Like a year down the line, it will continue to work. So that's a good, like, people choose Flyte for this reason. Scalable, Flyte is built on top of Kubernetes. It could scale up to many containers, like thousands of containers, and run in parallel. So it's scalable, and you can iterate quickly because of the notion of things that run on your laptop. You just decorate some functions, and it runs on the cluster afterwards. So these are the fundamental key points people choose Flyte over the other orchestrators. And also, Flyte is open source. It's a Linux Foundation project, and it's all coded on GitHub, and there's a community around it. There's a Slack channel. Companies that put Flyte into production all talk to each other over a Slack channel, and so there's a community around it. All right, so what is Flyte, and how does it look like from a high-level overview? From like, well, people write Python. Users write Python. It turns into a DAG. So the Python, in this case, is a workflow Python file, that's a workflow definition. It turns into a static DAG, and the static DAG gets run on a cluster. And it's always Kubernetes. So and Kubernetes are YAML files in my mind. They're just YAML files. So it turns Python into a DAG into YAML files, and that's how I see how the system works. Let's dive into it. Each of the node in the DAG is a task. These tasks have Python code. Any Python code you've seen so far, like in this case, load data or pre-process some data, those are tasks. A workflow is just a combination of tasks and describing how data flows between each task. So that also looks like regular Python. The data comes out of one thing, it goes passed into another task. Now, this workflow, when you run one command, pyflyte run remote main, like this file is called main. This builds a DAG and runs this on the cluster. It's one command line where it sends your code up to the cluster, builds this DAG, sends the code up to the cluster, and then runs it on one line. That's like the feel you get for a user. So the interesting thing about the DAG is that it's not a Python DAG. It's a serialized static graph that any language could read. And the backend is written in Go, so the Go is actually executing the workflow, which means so the external system is running the workflow that your user wrote. So in that design, since Python's not running the workflow and Go is, in that sense, it becomes more reliable because something else, you're not running user workflow code. The external system is looking at a static graph and running it.
So the workflow runs on a Kubernetes. Each task is just a YAML file, right? And I'm going to dive into like what's special about this YAML file that Flyte creates in this talk. So high level, Python DAG cluster, all right? So that's how I feel. That's how Flyte works at a very high level. No, so I'm going to dive into like the meat of it now. Like what's the magic? What's happening? I'll do it slowly. The first thing you want from a task is resources. So limits and resources are Kubernetes terms. Request is how much CPU or memory you need. Limits is the upper bound. You can specify them, and what happens underneath the covers is it populates a YAML file, right? And Kubernetes understands this YAML file, so it does the right thing. Another concept is you want more than CPU and memory. You want GPUs, like A100s. You specify A100, so your users specify A100s as a accelerator, and that's, in Kubernetes land, that's just a label. It's like toleration, but that's like a label, key value store. That tells Kubernetes, like, run it on A100. So it just populates the YAML file with more metadata so that Kubernetes knows where to spin up this work. Just a minor question, who here is familiar with Kubernetes? Okay, yeah, cool. That makes sense for you all to be here. So yeah, so YAML files. So simple. Now you want to run things with images. So there are a lot of systems where you have external systems build images for you when you deploy code. You could easily specify the code image to a string, and that just works. It does what you think. It spins up the pod with this container. For those that want to dynamically build images, there's an image spec abstraction where you specify what package you want and the registry you want to push to, and this it builds the image locally and pushes it to a registry. And underneath the covers, this is just like a Docker file generator, and it runs Docker build on it. So it's not too complex. It's one file. This is one Python file that does all this logic. So that's what Flytekit calls image spec, Docker file generator. This is a very neat concept about Flyte. It has something called fast registration, where let's say this is your task, and it imports other modules. Like your Python library could have many other files. How do we get these things up to the cluster? This is a structure. This is a very simple structure. There's only two files, but where I'm importing the other one, utils. And when I run PyFlyte run remote, it scans for all the imported modules, sees that it's in your directory, and if it is, it uploads it with it. So it intelligently looks at all the modules that you loaded and uploads it. So that it feels like you don't have to do anything else. It feels like it's local. And it uploads it to object store. Right? So you're going to see that. If you have a binary file, let's say this custom executable, it builds, then, and your task runs the executable, then you have to specify copy all, and this also uploads it to object store. So now, how does the Kubernetes runtime know about these new files that you uploaded? These files are compressed into a tarball on object store, and then in the entry point of your Kubernetes argument entry point, you specify where these things are, and then in the entry, and then we'll download it before your user code runs. So it downloads this tarball, unzips it, and then runs your user code. Then the next question is, how do you know which module to load? And in this case, you pass it. The entry point passes it more information. This is the workflow file, the module, which is here, and then preprocess is the task code, which is here. So it's specified in the entry point. That's how you know what to run. So that's how that works. Notice that I put typing everywhere in Flyte. This is by design. This is enforced. If the types don't match in Flyte, it will error before you run anything. Like when you try to run something, it will try to compile the workflow. Since the types don't match, it will error, and then you have to fix your type mismatch. And the strict typing is by design, and that prevents many other errors when you write Python. So the next question asks is, now that you have strict typing, how are these types stored? Literal types are like this ints, floats, strings. Those are Python types, and these are converted directly to what we call a flight literal type, because the flight workflow is a representation of the graph that independent of Python. So there's literal types that flight understands, and these are simple types that you just directly convert. These are also stored into object store as metadata. Right. Now, many people in Python like data classes. So data classes are just, you can have a data class containing these simple types and then use them throughout. These are serialized as message pack, and also stored into object store. Flight files are files, just random binaries that you want to output in your tasks, stored in object store. There's an API for it. You just return it, you return the type, and then you could open the file and then put stuff into it and return it. That gets serialized into objects. When you return it from a function, it gets stored in the object store. When you use it as an input, it doesn't download it right away, because this could be it's stored like a reference. And only when you open it and use it does it get downloaded in the task. Directories are like, it's a directory of files. In object store land, it's the prefix, and this is also stored in object store. These are just directories. And the nuance to this is that when you download, it only downloads, you have to call download to download it, because this prefix could be many, many gigabytes of files. So you have to be explicit about using these files. There's other types in Flytekit, like NumPy arrays. NumPy arrays what Flytekit has is an API called a type transformer, where you have to, it's an interface where you need to tell it how to serialize it to something that Flyte understands, and this gets serialized into a Flyte file, and also how to deserialize it. So the type transformer is a simple API where you have to tell it how to serialize the data and deserialize data. And then from there, there's a registration system where you register the type that this is how you deserialize and serialize a NumPy array, and then it knows what to do after that. So it's a plugin system for the types. Custom types, like polars, same way. You have to define, in this case, you have to install it with a plugin. It's serialized into the Parquet files at the end, but it's the same thing. You have to define deserialization and serialization logic. The way this works is it uses entry points, similar to fsspec, where like you define a namespace for your entry point, and then these get loaded when Flytekit gets loaded. So if the emphasis here is that all data is stored in an object store. That's like a design principle in Flyte. Like the metadata from your functions, your actual data, they're stored in the object store. It's called metadata and raw data store, but so this gives it, this has some features to it. Like this means that when you store things in the object store, it makes it easier to grab your data and do retries, because your state is, every time your task runs, the state is stored in the object store, and then you could keep going from there. It's like, so that's object store. Another thing here is that with object store and passing things around, the location of object store matters, because when you have a workflow, they run in different containers. And all the data is in the object store, so they get passed around. Every time you run a task, it gets stored in the object store, and when a task starts, it reads from the object store. But every time you run it, the locations of your objects must be different, because let's say you run something 5 days ago, and you run something today, you don't want it to overwrite the data from 5 days ago. So you want these object stores prefixes to be unique. And that means they're dynamically defined, and in the Python library, it's defined with templates. So these are templates to like, where do I want to put my data in object store? So when these templates are then stored are placed into the entry point. And so in this case, this is like .inputs and .output prefix, and these are templates that the backend would put the prefix into. Like for example, here, so it's just an S3 prefix. So notice that there's inputs and then an outputs prefix. Inputs is just the input to your function. It gets serialized into a protobuf. And So that's it. Like, so the inputs are a series of protobuf. Outputs of your function are stored into outputs. There's an output prefix because you can have more than one output. Errors are considered outputs too. And when you, in the UI for Flight, if you have a task that gives an error, we write the error into the UI so that the user could see what the error is. So these are written to errors.pb. Another fun thing is that Flight also allows users to write visualizations. So this is called Flight Deck. So where you could render different HTML files into the UI. And these are also stored as outputs. So these are stored as static HTML and deck.html. So that's Flight Deck. And a fun thing about decks is that you could also put them into the type system, where you can annotate a type, output type, to have like a renderer. And then if you tell the renderer how to change your type into HTML, it does it for you and then renders it into the UI. So it's really putting more logic into the type system because Flight likes type systems. So with everything in object store and save there's retries are easy. So let's say like when you run a workflow with 10,000 tasks, things fail and you want to retry. And since everything is saved in the object store, you could quickly retry. And then from the SDK, you just say retry equal 5. It will retry 5 times before actually erroring. There's also caching. It's simple because everything's object store. So you could just read from the object store to restore from cache. So the design of object store makes these things easier. So, and like if you scroll all the way back, the design of having object store storing states means that it's very language agnostic. None of this is Python specific. So you could write shell tasks using the Python SDK to just, as long as it reads and writes from files and directories, you could execute some random script, and that would be a task. So it's language agnostic. So if there's people write Julia with it. Each task could be Julia. It could be R. It could be some C++ executable. It runs in the task. When you design an orchestrator, sometimes you have dynamic runtime variables. Something like if you want to upload some tracking data to weights and biases, or Hugging Face if you're uploading a model and you want to store execution metadata, this is exposed to a current context. And how this works is it's just environment variables. It just interprets environment variables and then stuffs it into the context so that you see it in Python. And for those who need full control of Kubernetes, and you love Kubernetes, there's also something called a pod template. It's just a mirror reflection of what a pod spec is, but in Python. So this is when you want to just write Kubernetes-like code, but with Python-like SDK. So we support that with a pod template. So one of the key features of Flight is scaling up. So in this case, I have a function called preprocess, and if I want to map over many data sets, I could map task the preprocess function task, and then call it, and this will just scale. This is run preprocess on 10 containers in this case, and then each one preprocessing data set. So that's one quick way to preprocess in Flight. But there's other ways to do this. There's DAS and Ray and Spark. These take advantage of the Kubernetes operators, like kuberay, DAS Kubernetes, and Spark operator. That's what I use internally. So you could write DAS, Ray, or Spark jobs, and then spin it up in Flight. I'm going to give an example of Dask. Dask has a scheduler and workers. You can specify how much you want in the task. In this case, you have to install it with a plugin. And the way this works is it spins up a Dask cluster for that node. So let's say this one node is trained Dask model. It starts up a Dask cluster. It runs the computation that node describes in your body of that function. After it's done, it spins it back down, so there's no Dask cluster anymore, and then continues Flight execution afterwards. So this is how all this is for Dask, but this is the same for Ray, same for Spark. It's the same idea. It spins up cluster, spins it down, and which is very good for if you care about not leaving clusters running. Right? It spins it up and spins it down. So that's DAS. That's how it works underneath the covers. So how does this whole thing work? Remember, there's a task config option, and what the DAS object is just a data class. So that doesn't provide much logic, right? Data class doesn't. So the data class was just schedule and work group, but the actual logic of configuring DAS is it's called a DAS task, and it's also a plugin mechanism where you register the DAS class with the DAS data class object, and then internally there's a get custom function that returns a dict that looks at the data class and then forms a dictionary that the backend understands to create that DAS cluster. So it returns a dictionary. So that's how that works. And it's the same pattern for the other executors. For the task config, in this case Spark, you have Spark-specific configuration here, and then whatever's in here runs in the Spark cluster. Ray, same idea. You have a Ray config, and Ray has their own specific Ray configuration options. And this spins up a Ray cluster for that node, runs your Ray job, spins it back down, and continue. And then you could, in this system, that means you could have one node run Ray and then finish, and then another node run DAS, and then another node run something else. And you can have different systems all managed by Flyte and Kubernetes. Also PyTorch. So any of you do like multi-node training, this also spins up multiple nodes for PyTorch. Underneath the covers, it uses torch run, and it just runs PyTorch, torch run. So same idea, spins up torch, costs many nodes for torch, runs your training job, spins it back down. So that's like a very quick dive into Flyte. The objectives was write code in Python, convert it to a static graph, and then run that DAG in Kubernetes. And I think it's a very nice system, like as a design. And like I see many of the same ideas in other orchestrators, where you want to bring code from your local machine up to a cluster. Like these ideas are very common, so I hope it's useful. I didn't cover a big chunk of Flyte, which is the backend, which I recommend. If you want to learn about the backend of Flyte and how the operator in Kubernetes work, I recommend going to this link. There's a lot to it about keeping the system going in the back. It's a fun read. It's for an afternoon. So I recommend reading if you want to learn about the backend architecture of Flyte. And this is the part that's different between each orchestrator, the backend. So let's why Flyte? It's built on top of Kubernetes. The workflows are static, which people like because static graphs traditionally you can anticipate what's going to happen. They're more reliable. Embrace Python typing so that if you mistype things in your tasks, you get errors before anything runs. So the static typing is very useful. It's scalable. It could run on GPUs. It could run on the distributed platforms like DAS, Ray, Spark, and PyTorch distributed. You can map tasks if you want first-party support for parallelism. You can iterate fast because you can make your local code go into remote very easily with one command. The code gets uploaded on demand when you run the CLI. So it feels very quick when you iterate on a Flyte, when you're developing on Flyte. And yeah, that's Flyte. Thank you all for listening. This is lots of learnings and Flyte, and I hope you had fun diving into Flyte internals. And the code is available with that link, QR code. Yeah.
Great talk. Okay, we also have plenty of questions, which is great. Okay, again, going by a number of emojis, we have a question from Nick. Who is the target audience of Flytekit in terms of the Kubernetes expertise? For example, will a beginner drown in debugging K8 errors in YAML? Will an expert find that this is a frustratingly leaky abstraction that obscures the features they are trying to reach for?
The target user is not a Kubernetes expert.
So it's someone, like all the YAML file things I've shown is going underneath the covers. For a typical user flight, you don't want them to touch that. You don't want them to think about it. So they're using the Python SDK, using resources, and not thinking about the YAML files. That's the target audience.
Great. Now we have a question from Gwen. How does Flytekit interact with infrastructure as code tools like Terraform on different cloud platforms? For example, AWS, GCP, Azure.
It doesn't. So you have to use for most teams. I've seen they use Terraform to spin up their flight cluster, and then you use namespace. You use Kubernetes concept. You have a platform engineer that spins up your cluster, and they put restrictions on how much your team can use using Kubernetes native resource limits. And from there, the user doesn't touch Terraform. Yeah.
Okay. We have a question from Jared. With all the object store interactions, are there scalability issues? For example, are there limits on the number of accesses to S3 per second?
Yeah, so with so much access to object store, you get the traditional limits you get from Interact Object Store. The way I've seen teams work around it is using mount points. There's different ways to mount object store things into your pod, and those are workarounds. But you only reach them when you reach that limit. Like for normal operation, object store is good enough for many use cases.
And we have a question from Natty. Are there overheads building the DAG? In which situations? In what are situations in which this might become a problem?
The DAG is built locally. Can we repeat the first part?
Are there overheads associated with building the DAG?
There is no. When you write the DAG in Python in the Python workflow, there's no overhead. Like it's very minimum compared to running the DAG. So no, there's no. I don't have. You're running Python and. It's okay. It works.
We have a question from Angus. How is your project funded/run? For example, are you VC funded? Do you have like government stuff, docs and stuff?
Okay. The flight is largely funded by a VC startup called Union. And they employ many of the maintainers, and they made it a product. And so it's partly funded, but they have customers, which is a business, and they're funding development of the open source project too. Yeah. It's called Union, union.ai.
Okay. We got two more, and we got 2 minutes, so I think we're good. Okay, Ali asks, how are environmental variables handled? How can I ensure that my tasks have access to credentials?
So the most common way to access credentials is using the cloud providers. Like for AWS specifically, like you have IAMA roles that you can attach to Kubernetes. The pods that spin up Kubernetes, you can attach roles to them, and then you give them different types of access. So and then this is usually by your platform engineer. You don't want users to change access. Like you have platform people give you access to things. That's usually the workflow.
Okay, and then Ryan asks, this feels like a cool interface to deal with YAML and Kubernetes. But can you do a very short kind of overview about how DAGs work and how they and how the DAG interacts with all the other components? But you've kind of covered that, and this was earlier. This is a little bit earlier, but maybe you could just restate what a DAG is.
A DAG is it's directly acyclic graph. I could say, okay, which is directly acyclic graph. No cycles.
Yeah, no cycles in your graph. Yeah. So. Yeah, you had one of the, I think you had the slide twice to kind of, yeah, you just passed it.
Yeah, I think this one, DAG.
Yeah.
No cycles, arrows, point from node to node.
Yeah.
Yeah.
Yeah. Okay, so, all right, I think we are at time, and we have also answered exactly all the questions, so good job, everyone. Thank you, Thomas. And yeah, that has been it for the we got Paul with a, oh no. So that has been the general track for SciPy 2025. Thank you so much, everybody, for coming out and participating, and let's also give a big round of applause to Thomas and to all our fantastic speakers.